information. दूसरी क्लास में पढ़ी है.
कोई दिन में वो 12 बजे से करना है. At dot time they should speak from their class. So 5-10 minutes.
How are you? Shiv, how are you? Everyone is fine. We have time today. Can we have 5 hours class? Correct. Then I'll take a flight. When I was in Brazil, some 14,000 kilometers away from here, then came back. When I came back, Sunday, and this afternoon. So anyway, I think we'll have a travel log also at some point of time. मेरा भाई मुझे बता रहा था, my younger brother was telling me that the first travelogue, you know travelogues? People who write about their travels, going to different places, extremely fascinating. And when I was young, I read the first travelogue by Muhammad Akhtar Mamuka from my native place, Bahawalpur. And he wrote about his travel to Paris. And the name of the book was Paris 40 kilometers. If you get the chance, write Paris. And that was my first travelogue. But anyway, my brother told me that the first travelogue was written in this part of the world by a person called Raj Mohan Kulkarni from Delhi. And he wrote about traveling to different places in the world. He wrote about, he met with people in Europe, Africa, Australia. He met with people who were half animal, half human. He wrote all this with absolute confidence. This travelogue was written in Urdu and was extremely popular. The man has never left the city of Delhi in his life. So he just cooked up the stories of traveling all over. So this is fascinating. But I have traveled so many. I just tend to forget. I think at some point of time, I need to collect my memories if I can. Because I traveled to something like 70 countries in the world. My first travel was when your father or mother were born back in 1980s. And my first travel was in Turkey when my father sent me there. And then I came back after years in London. Since then, I've been traveling and traveling and traveling. After second, how many people like to travel?
I want one question.
Yeah, you have a question. I did go to Yemen.
For once, I went to Islamabad by airplane. Okay. When I back, I see the wedding of my mother there about this. The airplane was not, they have the ambulance there. I was so scared there. I remember you. The people go back. And I forgot for what time.
Okay, so when you are in a plane, then you keep reciting the Ayatul Kursi. And remember Allah subhanahu wa ta'ala, you get stuck in some air turbulence and feel like this. So
sometimes Stewart also made us scared.
It was here in Pakistan. I can imagine when this airplane was here. I traveled many times.
Are you planning to go back Yemen by boat.
No, but you know the way to do by train.
Yeah.
You know that
It's not so. I so my travel this time was extremely interesting because I used to come to South America from US, and this time I traveled through Dubai. So you take a flight from Dubai. Today's lecture is about travel outlook. And then we went over Saudi Arabia, crossed Egypt, Libya, came down to Sudan, Chad, and then to Nigeria, and countries like Guinea. And I think we crossed Guinea, Conakry, and then we came down, crossed Equator, uh, traveling towards southwest, and then crossing Salvador, going down to crossing over Amazon, and then coming to Rio, which is about 3,000 kilometers down to Equator. And so this was a route. And it was interesting because something like 14, 15 hours flight. We have nothing to do. We just think about it. And plane is like this also. But the worst travel I had was only recently from in Pakistan, and this was during this rainy season. My family was with me. We were coming from Islamabad to Karachi, and just before 10 minutes before landing,
right. Just 10 minutes. And it take 1 hour. So azab.
and the plane, well, it was air pocket, and then everybody was started reciting, and it was scary. But anyway, okay.
The previous, then now we have Wi-Fi all the time freely available. So previous when I was traveling, so I used like to send recite Holy Quran and everything. Now we are just busy important emails or
And watch movies.
yeah.
That's it.
Yeah, Netflix.
Yeah, one time I talked with Aditya when she was over Atlantic.
Yeah.
Yes, okay.
You said that you have visited 70 countries, and like in I think yes,
About 70 countries. I don't actually remember how many.
like I think you haven't visited Cameroon.
They have not visited Cameroon yet.
Cameroon, hello.
They invited me a lot. I met with Simon in who is from Cameroon. Okay, so
Most of the
I met with Simon
I haven't visited.
in Brazil, who was one of the first. You know him, Simon Comey. Okay, so he was among the first few. He received an award from me. I didn't go to Cameroon yet. No, I mean, it's that Cameroonian are not so enthusiastic to invite me. If they do, I'll certainly go. Right? I've been to Nepal so many times. But I think the Africa is exciting. I must say that I am just absolutely in love with Africa. It's chaotic, right? But yet extremely attractive. And the two people are very, very intelligent. We have all the time we have very, very interesting experiences. If you remember, I was traveling from Porto Novo, so Porto Novo, Benin to Lagos by road, and in this 250-kilometer travel, at least at 30 different places we were stopped. And each one of them were asking for money, and they wanted this money for Christmas. It was March. I said, Christmas is pretty far away. Why don't you just wait for a while? Okay. And again, I think Nigeria is exciting. I was I think it was in Abuja, traveling back to Islamabad. I was the last person to board the plane because they found something in my luggage which was objectionable and illegal. And they said that I have taken some very precious antique which represent Nigerian history, and I was taking away for. It was just a gift someone gave me, and they said this problem can be solved if I cooperate. Which of course I did. So, and then finally we realized that I was not cooperating. So I was the last person to enter into the plane. And they let me go. And so I was very, very excited. But this is not the it doesn't really stop me to go to Africa. So I'll be to I don't know, I don't know now. NMR okay, of course I've been to Egypt maybe like 20 times. I was in Sudan. I don't know how many times. Well, then I went to a lot of very, very interesting places. Because I went to Mauritania, went to Morocco, Tunisia. I went to Senegal, Kenya, of course. I went to Chad, I went to Niger, I went to Benin, Gambia, Mauritius, Madagascar, South Africa, and so on. And you get a question multiple times. Uganda, I really love. Very, very interesting country. Of course, these are so beautiful countries. I think the most important part of human nature is the quality of people, and that is what attracts me towards Africa. The last country I want to go are the Western countries. Anyway, so all set for NMR? Okay. You don't want it's a election. So what is this?
So the relaxation is the pulse.
This is free reduction decay. Let me take you again to this very exciting journey. Okay, so you have, I'm sure that my colleagues have actually told you about, we have discussed pulses, we discussed what happened to this magnetization vector. And this magnetization vector, which represents the net magnetization difference, Boltzmann distribution axis, is called M naught, right? It's called longitudinal relegation and longitudinal magnetization M naught. And then you give a pulse, you bring it to transfer plane. Transverse plane is XY plane. And this is the observable, detectable plane. You can detect your signals only when it is on the XY plane, because the detector is on XY plane. Once you give a pulse, radio frequency pulse, 90 pulse, you bring that on XY plane. You know now that you can bring this magnetization vector to any place on XY plane by using the choice of your P1 from where you're actually giving the pulse. So you can bring it, you have this tremendous selectivity of bringing magnetization vector on XY plane. Okay. So we have all kind of selectivities, tremendous selectivities. You have selectivity of choosing an element. You have selectivity of even within one element, you can selectively bring one magnetization and the other are not affected. So you have so much of selectivity. You also have selectivity of bringing them to XY plane and then observing them. You have selectivity of bringing them on XY plane anywhere, minus y, minus x, plus y, whatever. Nothing like this exists in any spectroscopic technique. This makes NMR extremely exciting. So once you bring the magnetization vector on XY plane, this is your core interesting magnetization vector, which is dancing on XY plane. Okay. And then slowly losing the energy by relaxation, going up. And your detector is on XY plane. Okay. So your detector is detecting this movement, circular movement of magnetization vector in front of it. So, again, I told you that it is a very interesting difference in conventional radio frequency absorption NMR to something which is so different. In this case, you're not observing radio frequency. What you're observing is that this little magnetization vector, tiny magnetization vector, M0, which is representing the whole range of various frequencies, is actually passing in front of detector. And when it passes through in front of detector, then it gives a little spike, right? And that is the free induction decay. So this is the free induction decay. This is the free induction decay. And there's a lot of science in it. So imagine that we give a 90x pulse. Okay, it comes to Y. Your detector, assume that your detector is on Y. You see a full signal, and then it goes, the magnetization vector goes full circle, and then it comes back to Y. It goes to minus x, minus y, plus x, y. It goes like this. Okay. So it is okay. So if it is right on, if your detector is on Y, you see a full signal like this. It goes down. It is on the other side. It comes up. It goes down. It comes up. It goes down. Okay. If you give a 90, if you give a 90 pulse from minus x side, where it will come? Minus y. And your detector is on y. How would you see your signal? The detector would see your signal you see the starting point? It is from the back. Okay? So you are a detector. Okay? I'm a signal. If I come in front of you with 90x, you see me by face. Okay? If the detector is on y, but the signal comes on minus y, then you will see my back. This is the back. Okay? It's called phase. So in this case, you see a different shape of the signal. In this case, you see a different shape of the signal because the starting point is different. Okay, so this is the kind of
Excuse me. As I know, you said this tube is rounding, moving in round. A bit of time.
what is moving now?
This tube, you
Test tube?
NMR.
NMR is not.
I mean, the sample is moving around here.
You forget the sample.
So if it is rounded, so what the benefit of this axis now? I come from the side, the sample will turn around. Say, can you understand?
I'm trying to understand. Okay, so
The sample is moving this way or not?
okay, so you need to go deep down in sample now. You forget the tube. If you don't forget the tube, nothing will be. Now you are on a nucleus spin, right? Nucleus spin. The spin of nuclear. And these little magnets, this nucleus, little magnets are vectors. Okay? Under the magnetic field, these vectors orient themselves aligned or opposed to the magnetic field. Dipolar or quadrupole, they can have different. Okay? And these magnets, these vectors, both energy states are equally correlated. Slight difference in population is called Boltzmann distribution axis. This Boltzmann distribution axis is called M0, bulk magnetization vector. This bulk magnetization vector, when you give a radio frequency pulse, a short burst of energy, they come on XY plane. So they are on XY plane. Now you are actually detecting this signal. And that is a free induction decay. Your detector is detecting this signal which is on XY plane and it's relaxing back, because it has to achieve thermal equilibrium. Thermal equilibrium is without radio frequency is up or down, right? The slight axis. You have disturbed this equilibrium by giving a radio frequency. When you give a radio frequency, you rotate it to XY plane. This XY plane transfer magnetization has to go back to longitudinal, right? By a relaxation mechanism which is divided into parts. One is called T1, the other is called T2. This relaxation process is monitored And that relaxation process is monitored by a detector which is detecting the signal. When it is on XY plane, it's going up. Okay? Done? So this is free induction decay. Okay? And why this is going less and less?
Spin or spin up.
Don't worry about that. Why it is tapering down? Why it is decaying? Why this full signal is becoming smaller and smaller, smaller, and then eventually become linear? Why? Moving away from that side. So they're going up, right? It's achieving thermal equilibrium. So the signal which you have is called free induction decay. This is your NMR signal. If we have 5 different types of protons in your molecule, you would have 5 different lines. If we have 20,000 protons in your molecule, you would have 20,000 lines. Okay. In ethanol, how many lines you would have? 3 lines. Okay. You brought them back. You brought them to XY plane all together. It's called coherence. So they are coherent signal. You brought them on XY plane. They are at the same place when you give the pulse. But after some time, they split. Right? They split. When they split, they have a different Raman frequency. And when they have a different Raman frequency, their movement on XY plane is going to be different. So you would have not 1, but you would have 3 FIDs. Okay, so they call time domain. They call time domain signals. And these time domain signals are transformed by a mathematical process called Fourier transformation into frequency. Understood? Now let us read. FID are exponential decay in time domain. You know, you're not measuring frequency, you're recording time, how long it takes to decay the signal, right? And then they are analogs. They are lines. And these lines cannot really be calculated, so they need to be converted into numbers. FID, free induction decay, these lines, remember in mathematical process of computer, you cannot do any mathematical process on lines. They need to be converted into numbers. Mathematics can only be done on numbers, right? So this is called analog to digital conversion, ADC. This takes place in computer. The computer converts FID into numbers. And those numbers are then Fourier transformed. Fourier was the name of the person who developed that mathematical process which convert these numbers, time domain, into frequency domain. Okay? It's called Fourier transformation. And then I told you about hypotization. So I don't know whether I should confuse you or not, but I like to confuse you. Okay. This is your free induction decay. You like it? Okay. And from here to here, this is time and amplitude. Nothing but time and amplitude, right? The difference is the phase. When you start your detector, where your magnetization vector is on XY plane. If it is on -y, start from there. If it is in plus y, start from here. This is first difference, called phase difference. Second, depending on the Larmor frequency, this amplitude would be different. The third, the decay would depend upon the kind of relaxation called T1, relaxation time. So they're going to be very deep and depends on various factors, including solvent, neighboring protons, and others. And you get this. Free induction decay is the NMR signal. This is what you get.
In ethanol, you have three different. How we are calculating their decay? How you can do it?
All three of you come.
I am with both.
No, please come. I don't want to use board, I want to use people. Okay. Your choice. Who's OH?
I am always.
No, you're not. You're CH2. Okay. These are three vectors. Boltzmann distribution axis. They exist down there also, right? But they are three vectors. I give them and I want a detector also. Where is a detector? Up the ship line. Up detector, okay. All three of you are different. Why are you different?
You're ethanol or what?
Yeah, you're ethanol. Why are you different?
I have CH2 here, CH3. The shielding is not.
Why three of them are different? Why are you different from them? Let's speak loudly here.
If I yourself, so the electronegative ratio of oxygen will be affected on me more than the CH2 proton, more than the HCl3 proton.
So you're different because you have inductive effect over oxygen, right? Oh, why are you different from him?
Simply when I am CH2, the environment about me, I am shielding different about him. He has near polar to the oxygen, but this electronegative to the electron. For me, when this small effect.
Avoid, because this is not direct. Why you are different?
Because I am totally far away from the O and I am shielding.
Tell me whether you would have Larmor frequency faster than them.
Yes. Well,
Why?
I would get with frequency easily than shift.
Why your Larmor frequency is faster than them? More Larmor frequency.
Because I don't have many electrons, I don't want.
Okay. Be effective more, right? That's why your Larmor frequency gets it.
And let me get
Let's see.
Now these are three vectors, right? And I bring them to XY plane. They're on XY plane. They're together. When I give a radio frequency, they're together. Because I give them a strong pulse, they're together. After I terminate the radio frequency pulse, they will start moving with their own Larmor frequencies. You start moving. I want you to move in circle. You're a detector, you see them together or different? Different. And if you're recording their decay time because they're going up also in the heaven. Okay. So when they're going up, so you see them differently. You see this, right? And please keep doing it.
Oh, I can.
Keep doing it. It's a good exercise. So how many FIDs you see? Total three? Three FIDs. Because three filament reactions. Okay. And the signal is now split into three and it's going up. Understood?
Question for one of us. How is the second two are different here? The shape. To the dark, up to the dark, or smaller. How the difference between them?
Who is faster among three of you?
Yes.
So he would be different.
That means he will be
Yeah, this he would move faster on XY plane.
spin excuse me. One of us. The second, how will we be?
No, I think it's an interesting question which we need to answer. Assume that this is CH3.
Yeah.
Okay. You saw CH3, right? CH3 up here. In front, right? You're here. So somewhere here you start. Because you're not right in front of her. Because you split it, already split it. You know, you split it in three parts. Okay. And he's the fastest one. Okay. And he has already crossed and gone into, when you turn on the detector, he's already on the negative side.
Clear, even separate or
And the phases would be different. Okay, this is a serious discussion. It's an important discussion. You see, you bring them together at the same time. You turn on the detector after they split. They already split it. They have to split because they have a different Lambert frequency. So they have to split. When they split, they would have a different speed because the Lambert frequency is different. So the XY plane, they would be in a different position. And when the detector is on, the detector will see them at different places, right? And with different speeds and with the different times. Because their thermal equilibrium, their relaxation would be different. They are different. Okay? And there were going to be three different FIDs, three time domains, three phases, three different amplitudes. And now, when you convert this into frequency domain, you would have a signal like this. Okay?
only one number. You don't have many numbers. One number, only one.
No, it's that's I'm not really clear. Understood?
Thank you so much.
You're welcome. Thank you for asking this. Okay, so FID, the time domain signals. Time and domain signals are converted to conventional frequency domain signals by a mathematical process called Fourier transform. So this dancing of FID, which is time, how much time it takes to go to thermal equilibrium. It's no frequency, right? How much time it takes that they each one of them go back to thermal equilibrium is recorded. And that time is converted into frequency by using Fourier transformation. And before that, of course, I told you that lines need to be converted into numbers in order to give you mathematical process, because lines cannot be calculated. The mathematics can only be applied on numbers, always remember. Right? Okay. अब कोई चलता नहीं है फिर इसका टिप्पी दे रखना पड़ता है नहीं स्लाइड्स चेंज करें Here you can see what I was trying to say. Okay, this is M naught. You give it a 90x pulse. It is on transverse plane. Your detector is on the Y. And this is going to be splitted because there are two different signals. For instance, this is one FID. You get a Fourier transformation, you get one peak at 5. Right? You converted FID into frequency domain. This is the second FID of the second proton. Okay. You get a peak at 7.5. If they are together, right? They are recorded at the same time. And when you record them same time, you have something like this. Because these peaks are interfering constructively and destructively. And you get two peaks, 5 and 7. If you have 20 protons, this FID would look more horrible. And you would get 20 peaks. Understood? Okay. This will look like this. You don't like it? Okay, so this is the FID of so many signals together. So many FIDs together would look like this. But computer is capable of differentiating each peak, converting these signals into numbers, and then giving you the frequencies. That is how things move. So, for instance, in this case, you get, roughly about 3 peaks, and this is the conventional NMR. So, it's kind of, as I told you, that the modern NMR spectroscopy is pulsed Fourier transform method NMR, because it is based on pulses, different from the conventional historical NMR. Second, that you don't record frequency directly, you record FID. And that FID need to be converted into frequency by using Fourier transform. So the NMR is called pulse Fourier transform. So what are the advantages? It is of course computer based. you cannot really do anything without fast computing. There are a lot of computing which is required to deconvolute this very large number of FIDs, and then to convert them into numbers, and then to convert them into frequency. Second, some of these protons relax from their excited state into thermal equilibrium in seconds, right? So it just takes seconds. The excitation pulse, which is 90x pulse, data collection FID, and conversion into Fourier transformation takes only a few seconds. And the data is collected, and you can repeat this cycle. So this is the advantage. Now, what is the advantage? In conventional NMR spectroscopy, continuous wave, you are standing and you are changing the frequency for hours. Here, you excited all of them together. You recorded their reduction decay. Your computer has converted them into frequency. You wait for a while, it's called 5T1 time. I'll explain that to you later. So they become fully relaxed. Then you give 90x pulse again. They'll come like this, right? You again record FID. They go back. You give another 90x pulse. You record FID. They go back. And you do it infinitely. In few seconds, one experiment is completed. In half an hour, you can collect maybe about 600 or 700 skeins. They call skeins. And when you collect so many skeins together, and if you have so many FIDs in frequency domain, I told you that signal to noise ratio will increase. Because noise is random, signal is overlapping, right? So, for instance, you can see this in this previous. There are noises. You see noises? They are not real signals, but they are random. Every experiment would have a noise at different place, but signal would be at the same place. So the noise will cancel and signal will reinforce. So it increases signal to noise ratio. It is called sensitivity. The greatest advantage of pulse NMR spectroscopy was that without investing into hardware, without investing into much more large magnets and other, you can improve the sensitivity. Okay? Advantages. Now I want you to repeat this. What are the advantages of pulse Fourier transformation and NMR spectroscopy?
Take time.
Well, this is not the advantage of the process. Advantage. Why would you do that?
It takes you short time.
Save time for what? For home, for cooking, for dancing, or
For recording.
but this is a process. Advantage. One single answer. It improves the sensitivity. It improves the sensitivity, so what? Next question. If the sensitivity is increased because of pulse Fourier transformation,
Quality of results.
Yeah, that's the sensitivity.
Then
Why? I mean, if sensitivity increase, so what? साफ हो जाता है ये तो ठीक है but why the sensitivity has any reason for you to be happy?
Yes, I can do any more for little amount or big.
You can either can do samples with little quantity. Okay.
Also large molecules. I can large molecules. I can do any more for
Also, the
large
isomers can
What about C13? So before this, you need 1 ton of sample to get C13 NMR. Now you can do that in few milligrams because you collect so many spectrum, you combine them together, signal to noise ratio will improve, sensitivity high, you get your nice clean spectrum of C13, which were not possible to that level of resolution and sensitivity before pulsar, for instance. So it was a revolution by all means. If there is one most important landmark in the history of NMR spectroscopy is the advent of pulse. Because it was because of pulse that you are learning this magnetization vector. If there was no pulse, why you need to worry about where is NMR, where is your signal? You just give radio frequency, they excite, you get the spectrum. It is only because pulse that you need to know where it goes. It is because of the pulse that you know the phases. It is because of the pulse that you record time domain signals. It is because of the pulse that you convert time domain into frequency domain. It is because of the pulse that you can record so many spectrum in small, span of time. And that is because of pulse that you get a greater sensitivity. When you take a greater sensitivity, you can record sample in small quantities of sample, which were not possible. You can record spectrum of molecules, spectrum of elements which have a low natural abundance and low gyromagnetic ratio. Okay? Are you excited? Okay. This is actually the same question. Now, rephrase the whole thing. How it help in improving the signal to noise ratio? How pulse NMR spectroscopy help to improve signal to noise ratio?
because of the difference in the induction speed.
Not Fourier transformation. Fourier transformation is a part of the process. How pulse NMR spectroscopy help in improving the signal to noise ratio? Because you can record lots of spectrum. And when you record lots of spectrum, then signal strengthen, noise weaken. You understand this, what I'm saying, noise? What is noise? In NMR, what is noise? Is impurity signal? Solvent signal? Noise क्या होती है? What is noise in NMR? If you have impurity, is a noise? Because impurity is a real molecule. It will never go away. So if you have an impure compound, you can only spray. Pulse NMR spectroscopy will not help you. This is the real molecule. Solvent was not. Noise is that electronic disturbance. When you turn on the radio Paro, Radio Sana, or Yuane, or Khartoum, Port Sudan. Okay. So you know that there are noises. You can't clearly listen that. You further tune it. Noises are random, right? Because noises are why in NMR machine there would be noises. This is all electronics. Tremendous electronic fluctuation. Magnetic field is non-homogeneous. You know, you have such a stable magnet. Despite of it, they're still not homogeneous. They still have fluctuation. Your detector coil is all electrical coils. They would have noises. Your radio frequency oscillator, they're also electric coils. They would have noises also. Someone come with a mobile phone, you would have a noise. You would have so many of these noises, and if you can cancel noises, you can see a signal clearly. The good thing is that in every experiment, noise is going to be random, right? And the signal is going to be at the same place. And when you record the signal at the same place, noise clear, it means that you improve the signal to noise ratio, which is sensitivity. Sensitivity. Now, let me ask you a question. If I ask you to design, and from next lecture on, we will be playing with impulses. If we need to develop decoupling of CH3 in this molecule, which is ethylamine, ethylene, how would you decouple CH3? You don't want to see, decoupling means that you don't want to see CH3 and its coupling. What you will do? So simple.
Orientation of box.
Radio frequency can bring all of them on XY plane. If you have two radio frequencies, one on CH3, fix on CH3 frequency, and this radio is on all the time. It means that it is circulating, right? And you don't see this. And the other CH3 and CH2 and NH2 are on XY plane. Your detector will only see what is on the XY plane. If anything which is not on XY plane will not be seen. Your detector can only detect magnetization vector which are on XY plane. Okay? If by any means you can eliminate that from XY plane, it will not be detectable. Okay. Same if you have a complete proton decoupled C13 NMR spectrum. You don't want to see coupling of C13. You know that all C13 which are protonated have protons which are NMR active, right? So they are split into N+1 rule, CH3, CH2. If you want to decouple, you don't want to see coupling of proton in your carbon spectrum. What you would do? Same, you will have two radio frequencies, one for C13, one for proton. You turn on the radio frequency for proton, you turn it on, you don't switch it off. It is constantly saturating the protons. Protons would never come on X5 plane. And if it is not coupled, you see only CH3 carbon 13 signal, which is on X5. If you want to remove OH signal in the proton of methanol, what you will do? Irradiate OH. It's called irradiation. It's called irradiation. It's called constant saturation OH signal. And when OH signal is not an XY plane, among three of them, if I take Adil and circulate him like this, and only two of them are on the XY plane, you would only see them because Adil is circulating on Z, negative Z.
Never turn off its frequency.
Yeah, we will not do that for him. Okay, unless the experiment is complete. So you can easily, even from within the same elements, such as proton, you can distinguish them and irradiate them. Okay. God, this is so interesting. Rotating field reference. Shall we do it today or over? Lunchtime?
Lunchtime.
Okay, everyone. Inshallah on Saturday, I don't know where I will be. Probably I will be in Lahore. So I would come online and my colleagues would actually. अगली दफा इनको आप probes भी दिखाइएगा. ठीक है? Any question? Yes, sir. Okay.
Liverpool.
No, it's all right. I like it.
About you did about the path you can come from X or Y. How you can do that? Can the path directly we can think?
Okay, that's a practical question. How can you move radio from one place to the other? This probe, which they will show you, you don't really have actually this frequency are given by frequency coils, which are electrical coils, which convert electrical energy to frequency. They are in circle. You can select them from anywhere. And also there is no detector coil. The same radio frequency oscillator coils serve as a detector coil also. Once you turn on the radio frequency, you turn it off, the same detector coil, the same coil can be used for detecting. So it's a very simple electronics which is used. Okay. What is the detection limit of sensitivity in a complex sample compared to GCMS, which is more sensitive? Okay, remember that NMR would never be as sensitive as MS. Because in MS, you're talking about the entire sample converted into ions. Entire samples converted. In NMR, no matter how big your sample is, number one, you are limited by the fact that you can dissolve certain amount of compound and you cannot supersaturate. So in this 0.5 ml of solvent, you can dissolve only small quantity of sample. Even if you have lots of sample, you cannot dissolve it. You can dissolve only small quantity of sample. You understood? Second, even from that sample, The nuclear spins are both on up and a high energy state and low energy state. And the difference between the population is small, tiny, tiny. On top of it, you also have problems such as natural abundance in carbon-13, low baromagnetic ratio. So the sensitivity limit in NMR is much lower than any other technique. But this is a very, very comprehensive technique. There is no other technique in the world where you have such a flexibility and you get such information of the entire molecular architecture, the entire microelectronic environment. If you get a UV spectrum, you only know that there are some certain unsaturation sites. If you get IR, you know only these are functional groups. When you get proton NMR, you know how many molecules, how many protons, what is their chemical shifts, how many of them exist, integration, how many of them have neighbors, splitting. So this kind of information, the information content in NMR is so much that it is driving the development. Okay?
Yes, go.
Are they, there was another student. Remember you answered a question correctly. And this is signed by sir. There is
Which
another, yeah.
Which you mean they cannot buy biscuits. See, it's for signed currency note is not accepted. You can only keep it.
Yes.
Okay.
There is another one, but the girl is absent.
Okay. Thank you.
Thank you, sir.